You saw my video, hopefully the first video that I ever made on YouTube. Go back and look at it. In there you see that there's a science section that got removed thanks to my wife. So I thought I'd better do another science video so that you can have something to compare the different videos to, and I can just see which one people enjoy out of the probably 10 people that are looking at these. That's not going to be very statistically significant.
Okay, Miles.
Yes?
How is your poll doing?
Oh, not good. You know it's not a good idea when it's your first ever video.
I know.
You know?
Yes, it is never a good idea to do a poll unless you have at least 8,000 viewers for every alternate option.
Oh, I've got 4.5 options.
You need 36,000 views to get a statistically significant result.
Oh, okay. Thanks, Google. I'll think about that. Let's talk about quantum mechanics. You might think that science is done and dusted. You might think that because quantum mechanics and Einstein and all those people back sort of over 90 to 100 years ago have solved all sorts of amazing things and we have nothing left to do. That's not true. We essentially are just like we were back 200-300 years ago, where there are still lots of amazing things to uncover and discover. So get cracking. You can still win a Nobel Prize for discovering something amazingly huge and groundbreaking. It's not all over. For instance, let's have a little look at quantum mechanics. There are lots of different interesting little things that happen in this world, and if we understand the calculations you need to do quantum mechanics, then you can understand the phenomena at a much deeper level. But, and as accurate as those calculations are telling those things, there are still many, many things which are yet to be found out, and some of them are amazingly basic. So, for instance, the two-slit experiment, which is a very common one to talk about, so I'll talk about it too, just because I don't have to explain it in too much more detail, and I can make this quickly. As you probably know, you've probably watched a bunch of videos on this subject, and if you haven't, then I'm very honoured that you picked my video to look at first. That's amazing. You must have scrolled through hundreds of YouTube video results to get to mine and not looked at any of them and then looked at mine. Wow, that's amazing. Anyway, quantum mechanics says that particles, when you get down to a small size, are not points anymore, which is just as well, because if it got down really small and really, really, really small and a particle was still a point, that seems weirdly non-logical reality. It's like a computer program or something. And I don't think we're in a computer program. So as it turns out, you look down to really, really small, and particles are no longer points. That feels good. They're more like this knot. Now, to us, in our world, we think of a knot as that. See, that's a knot for sure. But when you interrogate the world of the very, very small, like atomic-sized things, photons, electrons, quarks, they are no longer points. They are spread out things, so a knot would maybe look like that. Where does the knot exist? Well, it sort of exists everywhere around there. And we can discover that this type of thinking is true by doing experiments like the double slit experiment. These little particles you send through one at a time, this is just one little thing at a time, comes through a slit, and when we used to think that this was a singular particle, it got really confusing because as it went through the two slits, it actually went through both at the same time, and then did a thing that waves do. Waves can interfere with each other, like the crest of one wave adds up to the other crest and they get double crests, and then you get bits where the two waves cancel each other out and get no wave. That happens, and it was happening with single particle, one at a time, coming through for all the world, acting like it went through both slots and interfering then with itself, a bit like having an argument with yourself, I guess. Bending because an interference pattern then actually makes a particle go in a different direction. This is a little particle. Let's just pretend this is the particle here. It comes through here. It goes through both slots, then interferes and goes off at some weird angle, different angles. And then it hits a detector. So we are taking a measurement. This is important. This a measurement here at the end, measuring where the particle goes. And because it's interfering with itself, when you look at where all the particles go, different particles end up going in different locations. And then if you add up all of those particles over time and start to see where they all go as a collection, you discover that they create a nice little pattern that looks like an interference pattern on the little detector at the back here. When you just add them all up and you see land on the detector at the back like that. So that would be, this is coming along here, goes through here, interferes with itself, and then maybe this one heads down this way. And then we detect it. We make a measurement. This is when we measure it. And no one talks about this, but we are measuring this particle at the board at the back. We put something in the way of this particle. It then has to deal with that thing. It has to interact with it. And at that point of interaction, it causes the knot to go back down to a pretty small spot. And we get a definite reading at a definite location, not spread out anymore. But let's say you want to detect the particle at this slot, just that slot there. Have a little detector just there. And this detector, it's a thing that can tell if the particle, an electron or a photon or proton, it can tell if it's gone nearby it. It feels its presence. And you can't just do that without interacting with something. Like you can't measure a wall without going to one end and putting a tape measure against the corner and going to the other end. You've sort of got to touch the wall. You've got to be in those spots. You can't do it without actually going there and doing it. So you can't find out if a particle goes through one slot or the other without actually asking a very small question of that particle to give up a tiny bit of its momentum or to push another little particle a tiny bit a certain way. So that's what measurement is. It's not necessarily just looking at something with your eyes. This is way beyond that type of thing. One of the little fascinating aspects to making a measurement of where this particle goes is it's enough to make the knot go to a small little knot at that spot, because we've asked a question of it, the particle. We've interacted with it here, and that interaction causes it then to come to a little spot, a little thing, which goes through one or the other slit. It can no longer travel through both slits at the same time because it's sort of too small. I think this is how I like to think of it. It's just too small. It only goes through one of those slits, and then it doesn't interfere with itself. So, and I'll have to undo it again because what you got to remember is once it's past that little slot and comes through it, it goes back to a thing like this again. It's not always a little spot. When you're not asking anything of it, it's like that. And then it travels, because it's not interfering with itself now, it then travels along a straight line. And then we ask it again at the end, where are you? And it says, I'm right here because I went in a straight line from there to there, and I'm right here. And I didn't change my angle, just went straight. Well, anyway, they all pile up. They all land just there, and the other ones go through the other slot, and they all land just there. Right? So you get two spots where they all accumulate because they only went through one slot. Because this act of measurement isn't just us looking with our eyes. We've got to actually tap the particle some way to find out where it went. The other fascinating little thing, which I think this helps illustrate a little bit, is that you only need to measure one slot, because this particle coming along initially, it's going to go through both. When you ask the question of the particle by having a detector on one of the slots, this thing feels it no matter which slot it ends up going through. It forces it to decide to be somewhere. Now, also another little thing, this is analogy you can do with this one. You can say, okay, I know, let's make it even bigger. I know the particle is somewhere between my two hands, but every time we pull the knot together, it ends up in a different spot, right? Not exactly the same every time. On average, it's halfway between, but individually, it comes out in a different spot. So back to this little slit, as it's traveling along here and it hits the little double slit thing, it does in fact know that the detector is on one because it's larger than both. It was going to interfere with itself. The detector is at one. That detector triggers this thing to go to a certain location. Now, where does it end up going to? Well, on average, it could be here or it could be there. It's sort of going to be somewhere between those two, and it ends up at one or the other. Sometimes it ends up at the one where the detector isn't, and you get the particle going through that slot, and it goes straight there, even though the detector didn't detect anything, because the detector, in however that operates, has caused it to go from being a big thing to a small thing, but in the process of causing that to happen, it also caused it to materialize at the other slot. So it ends up not detecting anything, which seems pretty weird that even the act of not detecting the particle is enough to make it stop having this interference pattern with itself. But it doesn't seem so mysterious when you look at it like that. Now, the thing that I find wonderful is that this process of how come objects, when they're very small, behave like this, and then they don't seem to act like that when they're really big. So we don't see apples that are smeared over space. But incidentally, they have made large molecules, so 2,000 atoms, behave like this. So there's something we don't understand. This is where, if you want to become a very famous scientist, you can start to explain how things that are small change to things like that at certain times, like when we ask a question of them or when we want to make them interact with something. Some of the theories include it only happens if you ask the right questions of it. These things are interacting with things all the time. When it goes through the double slit, it's interacting with many, many atoms that form up that double slit. That type of interaction doesn't break this. But other ones do when you actually want to sap a little bit of energy from it in order to find out if it went through one slit or the other, or when you want to sap some energy from it when you make it hit the back of the board and light up a little spot on the board. That is enough to collapse it to this knot. So is it the type of interaction that causes it to happen? Or is it the size of the object? Because when it's bouncing into something, it definitely does this. But is that because it's bumping into a much bigger object and that bigger objects can't sustain this? But as I said, there have been large objects, 2,000 atoms in size, that they have made to do this, and they think that maybe they can continue going and make even larger objects do this. But at some point, it must stop because we don't see things like this. Except there's another theory where they say, no, it doesn't stop. And in fact, this is all true, and we do see smeared apples, and we do see smeared everything, and all is existing in lots of different potential outcomes, except all those outcomes exist in slightly different universes, and that there must be a multitude of universes. And if we looked at all of those universes collectively, we would have this smeared out thing like this. But in one or the other universes, we have only one particular outcome that occurs. That sounds like a pretty interesting way to solve that problem. There are other much more logically sounding, sensible solutions. Maybe one, for example, is that gravity has something to do with it. and that once a particle is big enough to feel a pull of gravity, then it does that, which I think sounds quite nice because it also means that feeling the force from being detected also causes that to happen, and then explains why large objects which feel gravity don't exhibit this behavior. So the really interesting question is how we go from the quantum world where things are like this to our world where they're like that. If you want to solve that problem, I think you will end up being one of the very famous scientists of all time. And that problem's been around for a long time. So there you go. One science video done. I hope that made sense.